There are three main types of reaction involving alkenes that we will need to know for the A levels: electrophilic addition, reduction, and oxidation. In this video, I will be going through the various electrophilic addition reactions. For electrophilic addition, there are four main reactions that we are expected to know in the syllabus: electrophilic addition of hydrogen halides, electrophilic addition of halogens, electrophilic addition of water, and finally, electrophilic addition of steam. For the electrophilic addition of hydrogen halides, the reaction looks like this. We react an alkene with a hydrogen halide in order to form a halogenal alkane. X represents the halogen. The reagents that we will use for this reaction will be hydrogen chloride gas, hydrogen bromide gas, or hydrogen iodide gas, HCl, HBr, and HI. Also, the reaction will be conducted at room temperature. The reaction mechanisms for this reaction is as follows. I will be using ethene and HBr as an example. This is a two-step mechanism. In the first step, the electron-rich double bond will attack the hydrogen on the HBr molecule, which has a partial positive charge. This occurs as the HBr bond is polar and the bromine atom is more electronegative, hence pulling more electrons towards itself. This step will result in the formation of a carbocation intermediate and a bromide anion. This is the slow step. In the second step, the bromide ion, which is the nucleophile in this case, attacks the carbocation, which is electron deficient. This is the fast step, since the negatively charged bromide ion attacks the unstable and positively charged carbocation. This will result in the formation of our halogenal alkane, bromoethane. The reaction to this itself is rather simple. However, what if we are now adding a hydrogen halide to an unsymmetrical alkene? For instance, what if we add HBr to propene instead? Propene is an unsymmetrical alkene. Do you realize that we can form two possible products instead of one? We will be able to form both 2-bromopropane and 1-bromopropane. One of them will be the major product, and one of them will be the minor product. How do we know which is which? So now, in order for us to determine the major and minor product, we will need to know the Markovnikov's rule. So, what is the Markovnikov's rule? This rule states that in an electrophilic addition, where we add an electrophile to an alkene, the electrophile acts in such a way as to form the most stable carbocation intermediate possible. So, in this case, when we are adding HBr to our asymmetric alkene, propene, there are two possible intermediates that can be formed. Do you realize that one of the carbocation intermediates is more stable than the other? The carbocation, the one on the left, is more stable. The carbocation on the left has two methyl groups, CH3, attached directly to the electron-deficient carbon or the carbon with the positive charge. As the methyl group is electron-donating, it will stabilize the carbocation to a greater extent as compared to the carbocation on the right, which only has one alkyl group attached to the electron-deficient carbon. Hence, since the carbocation intermediate on the left is more stable than that on the right, this will form the major product, while this will form the minor product. In general, we can just remember that when we add a hydrogen halide to an unsymmetrical alkene, the hydrogen gets attached to the less substituted end of the double bond, which is basically the carbon with more hydrogen substituents. However, please do understand why this is so and not just memorize blindly. So, another important thing that we need to know is that the carbocation is trigonal planar in shape, or just planar in general. Hence, the nucleophile will be able to attack this carbocation from either above or below the plane. So, if the carbocation formed has three different groups attached to it, a racemic mixture would be formed. Let me use an example to explain this more clearly. I will be using butene and HBr. When we add HBr to butene, we get this carbocation, which has three different groups attached to the electron-deficient carbon. Probability-wise, the nucleophile has a 50% probability to attack from the top and a 50% probability to attack from the bottom. In each case, a different enantiomer of the product will be formed. Hence, as this produces an equal amount of two enantiomers, it will give us a racemic mixture. Now, the next reaction that we will need to know would be the electrophilic addition of halogens. For this, we will react an alkene with a halogen in order to produce a halogenal alkane with two halogens. Again, X is the halogen. The reagents for this would be chlorine gas, bromine liquid, or either chlorine or bromine, dissolved in CCl4, an organic solvent. Conditions required are room temperature and the absence of UV light in order to prevent free radical substitution from occurring. For the observations, if X is chlorine, the greenish-yellow chlorine gas will be decolorized. If X is bromine, the reddish-brown bromine liquid will be decolorized. For the mechanism, I will be using ethene and bromine as an example. In the first step, the alkene will attack the bromine atom with a partial positive charge. The reason one of the bromine atoms in the Br2 molecule has a partial positive charge is because the high electron density of the double bond would repel the electron cloud of the bromine molecule as it approaches the alkene. This step is a slow step and would form a cyclic bromonium ion and the nucleophile Br-. This cyclic bromonium ion intermediate is highly strained and hence very unstable. In the second step, which is the fast step, the bromide ion will then attack the unstable cyclic bromonium ion in order to form the product 1,2-dibromoethane. Again, this is the fast step since it involves oppositely charged species, which are the positively charged carbocation and negatively charged nucleophile. The next electrophilic addition reaction that we will need to know will be the electrophilic addition of bromine water. For this reaction, alkene will react with aqueous bromine in order to again form two different products. Once again, one is the major product and one is the minor product. Note that this equation is not balanced. The reagents required would just be bromine water, and this reaction is carried out at room temperature. For the observations, orange bromine water would be decolorized. However, this time, can you see that we once again have two products, a major and minor product, even though we used asymmetrical alkene? Why is that so? So in the first step, it proceeds just like the previous reaction, where the alkene reacts with bromine in order to form the cyclic bromonium intermediate and the bromine nucleophile. However, at this point in time, do note that there are two nucleophiles present, the bromide ion and water. Realize that since we are reacting the alkene with bromine water, water molecules are present throughout the reaction. Hence, both nucleophiles will attack the cyclic bromonium ion. Now, in the second step, similar to the first step, the cyclic bromonium ion will be attacked by the nucleophile. However, in this case, we have two possible second steps. Here are the mechanisms. The reaction at the top is the reaction where the cyclic bromonium intermediate is attacked by the bromide ion that was formed in the first step. The reaction at the bottom is the reaction where the cyclic bromonium intermediate is attacked by the water molecules that are already present. For this reaction, note that there will be an additional step whereby the bromide ion will remove a hydrogen attached to the electron-deficient oxygen in order to form HBr. Since there is a larger proportion of water molecules than bromine water, it will attack the intermediate preferentially, hence forming the major product. Do note that in such cases, when there is more than one nucleophile, the major product usually depends on which nucleophile is present in excess. Now, the final reaction that we will need to know will be the electrophilic addition of steam. Note that the previous reaction that we had gone through was the electrophilic addition of water at room temperature and not steam. So, for this reaction, when we react an alkene with steam, we get an alcohol. Again, there would be a major and minor product due to the Markovnikov's rule. In terms of reagents, what would be required for this would be steam. Also, do note that in terms of conditions, this will be conducted at 300 degrees Celsius, 70 atm pressure, and in the presence of a H3PO4 catalyst. Note that it is important to remember these reagents and conditions. So, if you have enjoyed this video, do remember to like and subscribe. In the next video, I will be going through the oxidation and reduction reactions of alkene.